Hello everyone, welcome to the session for quick revision of fluid mechanics. We'll continue with properties of fluids. And the next property of fluid is capillarity. So rise or fall of a liquid inside a narrow tube is called capillary action or capillarity. It is a combined effect of cohesion and adhesion of liquid particles. Okay, you see here. So here we have a vessel which is containing some water, and if you insert a capillary tube in that, there will be a rise of water. Okay, and this rise of water is due to a cohesion and the adhesion. Clear? And now from this point there will be a surface tension which is acting like theta with respect to the glass tube. This particular point is meniscus. We call this particular point as meniscus. And moreover, it is the level of water and it is the level of a meniscus in a glass tube, and that is your capillary rise. From the level of water, the formation of meniscus, the distance between these two is your capillary rise. And here you can see the conditions. Here the addition is greater than cohesion. That means if you are using water in that, your addition is more. Because of that, the meniscus is concave. Okay, that means due to this addition the capillary rise will takes place. And here the water is a liquid, and this liquid wets the surface. Okay, these 3 points are very important to understand how the capillary rise is taking place. The rise will takes place because of the addition, which is more than your cohesion, and the meniscus will form as a concave. Because of that, a capillary rise is more. And the next one is liquid wets the surface. That means water will wet the surface. And again, coming to this theta, this theta is equals to 0, nearby 0, which is less than pi by 2. That means which is less than 90 degrees. And now which the liquid surface which is raised, the surface tension of that is sigma, and we have a circumference of the tube, and that circumference is pi d. Okay, and mainly this capillary rise is due to cohesion and adhesion, and capillarity depends on surface tension and the angle of contact. Here you can see the angle of contact, and here you can see the surface tension. Right, now we'll try to solve this. The weight of the liquid of height h is, okay, whatever the water is taking from the height, from the meniscus to the level of water in the vessel, will take that quantity of water as area of the tube into h, which is volume into density into gravity, which is rho gv is your weight of the liquid. And what is the area? Pi by 40 square into h is the height for what you're going capillary rise is taking place, and density of water into gravity. What are the vertical component of a surface tension? And that is sigma, which is surface tension into circumference of your tube into cos theta. See, the angle is taking place in this way, but what is your vertical component of this? Which is force into theta, and that force into cos theta. Okay, here the force into cos theta. Here if you substitute that, the force is circumference into surface tension into cos theta. And by the equilibrium of forces, what you're going to get is, here the weight of the liquid, here it is the vertical component of the forces. If you simplify this, you're going to get the capillary rise as 4 sigma cos theta divided by rho gd. So for water, the theta value maximum it will be 0 for water and clean glass tube. The theta value is 0, and if you substitute that in the equation, you're going to get h equals to 4 sigma divided by rho gd. What is rho g? Specific gravity, right? Here specific gravity is, you can replace rho g with respect to specific gravity rho g, omega. And coming to the capillary depression, okay, if you take the mercury in the vessel, if you replace the water with mercury, then the capillary depression will take place, and this depression is due to the cohesion will be more when compared to the adhesion, and the meniscus what it going to be formed is convex. Okay, you can see the convex here, and now the capillary depression will be from the convex to the level of water. Okay, and moreover you can see the depression at this particular point. Okay, here the capillary depression is taking place. In the tube also it is capillary depression is taking place, and this depression is due to the mercury will stay away from the surface, and this is because the cohesion will be more when compared to the adhesion. And the theta value, the angle made by the surface tension with the tube, is theta, and that theta is greater than 90 degrees. So it will be for mercury, the theta value is maximum, it equals to approximately 130 degrees for mercury and the glass tube. And the capillary rise and depression increases as the diameter of the tube decreases. So if the diameter of the tube is less than 8 mm, so there will be a rise of or depression of your capillarity. That means the capillarity will increases. And the next one is capillary effect will be zero if the tubes are larger than 12 mm. If the tubes are less than 8 mm, then the capillarity will increases. Coming to the next property, it is bulk modulus. We can also call coefficient of compressibility or bulk modulus of compressibility or elasticity. And coming here, bulk modulus is designated by K, and it is the ratio of change in pressure to the volumetric strain. And change of pressure is designated by dP, and the volumetric change, which is the change in volume divided by original volume, is your volumetric strain. And it will be happens at the constant temperature. Here the vessel is there, okay, in that some liquid is there or any fluid is there. If you compress that, the pressure on it will increases, but the volume will decreases. That means it will become negative. To equalize that to positive, you are keeping that negative here. Okay, if you make negative will get cancelled, again you are going to get the positive value. So for the sake of convenience, you are taking this negative value. So this will happens at constant temperature. Now if you replace these terms, you are going to get K equals to minus V dou P by dou V, where temperature is constant. And here you can replace the volumes with densities. Then what happens when the compression is taking place, the density will increases, so it will become as positive. So that's why you are not taking any negative value here. Rho into dou P by dou rho at constant temperature, and the units for bulk modulus is Newton per meter square or pascals or kg meter per second square divided by meter square, and the dimensional units is m L to the power of minus 1 T to the power of minus 2. Okay, and this is about your bulk modulus, which is change in pressure by volumetric strain, and that too you are going to have the negative, and you can replace the volumes with densities, which is rho. And the next property is compressibility or isothermal compressibility. Here it is the reciprocal of bulk modulus, which is the compressibility or isothermal compressibility is designated by alpha, which is equals to 1 by K, and it is reciprocal of bulk modulus, and alpha equals to 1 by K, that equals to, if you place the bulk modulus formula here, you're going to get 1 by rho dou rho by dou P T, that equals to minus 1 by V change in volume by change in pressure at constant temperature. High value of compressibility indicates that fluid is easy to compress. When compressibility is increasing, that means the liquid is getting compressing more and more. That means there will be high compressibility when there is the easy fluid. And the unit meter square per newtons, or we can also write it as 1 by pascals. And the dimensions for this compressibility is m to the power of minus 1, L to the power of 1, T to the power of 2. And coming to coefficient of volumetric expansion, and this we can also call the volume expansivity, and it is designated by beta. So coefficient of volumetric expansion is a measure of change in volume with temperature at constant pressure. In the previous case, we seen change in pressure with respect to the volume at constant temperature, but it is somewhat change, which is like a change in volume with temperature at constant pressure. In the previous case, it is at constant temperature, but now it is at constant pressure. So now it is similar to the coefficient of thermal expansion of solids. So in solids, what happens, the change in length is proportional to the original length and the change in temperature. So when there is a change in temperature, there is a change in length, but that equals to your coefficient of thermal expansion into length into change in temperature. So in the same way, we are also taking like change in volume with respect to the volume. Change in volume is directly proportional to change in temperature. To equalize that, you're going to take the coefficient of volume expansibility or volumetric expansion, so at constant pressure. So if you substitute or if you simplify this, you're going to get beta is equals to 1 divided by V, your change in V with respect to temperature at constant pressure. And that equals to, you can replace this with densities, which is rho. See here, change in volume with respect to the volume is equals to change in density by density. So now you can simply remember this. Your compressibility is, bulk modulus is negative, compressibility or isothermal compressibility is negative, but your volumetric expansion or coefficient of volumetric expansion is positive. In this case, you can see here. So for this, and the next, coming to the units are per degree centigrades or per degree Kelvin, and the dimensions are just theta to the power of -1, which is theta is represents temperature. And coming to the vapor pressure, you can see the figure here. See, the liquid is half of your vessel, and if the vapor is taking place, if the vaporization is taking place, then your liquid molecules will escape from here and take place here. This molecule will exert the pressure on the free surface, and that is your vapor pressure. Okay, once we see here, liquid exhibits a free surface in the container. The molecule constantly escape out of the liquid surface and forms a vapor phase is called vaporization. So it will, the vapor molecules or molecules will escape out and form as a vapor molecules, right? And the liquid molecules escape out and form as a vapor molecules in the vaporization. But when some of the vapor molecules come in contact, they form liquid phase is called condensation. Again, these vapors come onto the surface, and by that contact it will get into condensation. So it will convert that vapor molecules to again liquid molecules. So consider a closed vessel. When vaporization takes place, the vapor molecules accumulated in the free space above the liquid surface. These vapor molecules exert pressure on the liquid surface. Vapor molecules exert pressure on the liquid surface. Thus, the pressure exerted by the vapor molecules on the liquid surface is called vapor pressure, and it is designated as P. Okay. And the next, coming to the cavitation, the pressure at any point in the flowing liquid becomes equals to or less than the vapor pressure. You have to remember this. If the pressure in a flowing liquid is less than the vapor pressure, then the vaporization of the liquid starts, right? Because of this, there will be a starting of your bubbles. You can see here, the bubbles of these vapors are carried by the flowing liquid into the region of higher pressures, where they collapse. So because of this collapsion, what is happening, we'll see. The pressure developed by the collapsing bubbles is so high, which erode the material or cavities are formed on a metallic surface. Hence the name is cavitation. And this action we call as pitting action, where there is erosion and the cavitation are forming, and that is your pitting action. See here, in a tube, a flow is taking place, a fluid flow is taking place, and in this, if pressure at any point in a flowing liquid becomes equals or less than the vapor pressure. If the pressure over at this point or at this point or at any point, if the pressure is less than the vapor pressure, then the vaporization take place and there is a formation of bubbles. And these bubbles will flows to high pressure. Okay, the pressure is high. Where the pressure is high, at that place these bubbles will collapse, and because of that the pressure developed will be high, and that pressure will erode the surface of your material And moreover, there is a formation of cavities on a material, and that is your cavitation, the concept of cavitation, and the action which is taking by making eroding your material and by making the cavities on a surface, and that action is pitting action. We'll continue in the next session. Thank you.